equatorial rings. These features suggest the presence of either an intense magnetic field or a binary companion influencing the star's evolution. If a secondary star is present, its gravitational interaction could be sculpting the expanding gas, directing it along preferred axes. This would explain the sharp edges seen in the nebula and the apparent lack of chaotic turbulence that typically characterizes similar objects. The central star is likely in an advanced evolutionary stage, either approaching a transition to a Wolf-Rayet phase or nearing its final collapse. The material ejected into space could be part of a larger process in which layers of stellar atmosphere are shed over time, forming structured nebulae that persist long after the original outburst. The exact mechanism behind the symmetry remains a topic of ongoing study, with hypotheses ranging from episodic eruptions caused by internal instability to a controlled expansion influenced by a strong toroidal magnetic field. Spectroscopic analysis reveals that the nebula is rich in both silicate and carbon-based dust, suggesting complex chemical interactions occurring within its expanding shell. The presence of ionized hydrogen and oxygen lines indicates exposure to intense ultraviolet radiation, which is slowly altering the composition of the surrounding medium. These processes are crucial in enriching the interstellar environment with heavy elements that later contribute to the formation of new generations of stars and planetary systems. The velocity of the expanding gas suggests that the nebula has been evolving for thousands of years, though it is unclear whether it has remained stable over time or if it has undergone significant changes in structure. Some researchers propose that the formation is an optical illusion, where a more cylindrical or bipolar outflow appears squared due to our viewing angle. Others argue that external influences, such as a dense interstellar medium or remnant stellar winds, may be reinforcing the shape by constraining material along specific planes. Advanced telescopes equipped with high-resolution spectrographs are expected to provide more precise data on the velocity distribution of gas and dust. By analyzing how light interacts with different regions, astronomers hope to reconstruct the three-dimensional shape and determine whether the observed symmetry is an inherent property or a temporary phase. If the central star is approaching a supernova event, its surrounding nebula could dramatically brighten as the explosion interacts with the ejected material, similar to what has been observed in other massive star systems. Comparisons to other structured nebulae suggest that mass loss in massive stars follows patterns that are more organized than previously thought. While planetary nebulae often display symmetric forms due to the expansion of shells around dying stars, this particular object exhibits a level of precision that challenges conventional models. If magnetic forces are indeed playing a dominant role, it may suggest that similar structures could exist elsewhere but remain undetected due to their orientation or distance from Earth. Infrared observations have also hinted at the presence of complex organic molecules within the nebula, which could have formed through photochemical reactions triggered by high-energy radiation. Such environments are thought to be crucial in the early stages of planetary system development, as they contribute to the formation of prebiotic compounds that later become part of interstellar dust clouds. Understanding how these materials evolve in different stellar environments provides insight into the chemical diversity of the galaxy. Future research will focus on mapping the precise movement of gas within the nebula and determining whether external factors are influencing its evolution. If a binary companion is confirmed, it could provide further evidence that multiple star systems are a key factor in shaping structured nebulae. Long-term monitoring may reveal subtle shifts in brightness or morphology, indicating ongoing dynamic processes that have yet to be fully understood. If the central star eventually undergoes a supernova, it could transform the surrounding region by sending shock waves through the nebula, triggering secondary reactions and possibly altering its structure. The resulting supernova remnant would provide valuable data on how pre-existing mass loss affects the aftermath of stellar explosions. If a neutron star or black hole forms at the core, it may interact with the surrounding material in ways that produce additional high-energy emissions, making it a potential source of radio waves or X-ray bursts. The precision of the formation continues to challenge existing astrophysical models, suggesting that either previously unknown mechanisms are at work or that magnetic shaping plays a far greater role in stellar evolution than currently assumed. Upcoming telescopes with adaptive optics and interferometry will provide deeper insights into the processes governing the expansion of ionized gas and the interaction between radiation and dust within the nebula. While its ultimate fate remains uncertain, its significance as an astrophysical case study is undeniable. Whether it is a short-lived phase of stellar evolution or a long-standing feature that will persist for thousands of years, it represents a rare and valuable opportunity to study the forces that shape the most massive stars in the cosmos. The answers it holds could refine our understanding of how stars evolve, how they lose mass, and how they influence the galactic environment over cosmic timescales. The forces responsible for shaping this nebula remain a subject of debate, with multiple mechanisms potentially working in tandem to maintain its strikingly structured form. The presence of a dense circumstellar medium suggests that earlier mass ejection events may have interacted with surrounding material, creating shock fronts that reinforced the observed geometry. If stellar winds or episodic eruptions from the central star were directed by an unseen companion, their effects could have compounded over time, gradually sculpting the nebula into its current configuration. Magnetic fields are another possible factor influencing its development. In some high-energy astrophysical environments, magnetic pressure can guide ionized gas along preferred paths, constraining outflows into collimated jets or symmetric lobes. If this phenomenon is occurring here, it could help explain the sharp definition of the nebula's edges and the near-identical structure on opposite sides of the central star. Observations of other massive stellar remnants have shown that even weak magnetic fields can have a profound impact on outflow dynamics, reinforcing the idea that this nebula's shape may be magnetically driven. The chemical complexity of the surrounding gas adds another layer of intrigue. The discovery of molecular hydrogen and polycyclic aromatic hydrocarbons within the nebula suggests that the region has undergone prolonged exposure to ultraviolet radiation, leading to chemical reactions that produce complex organic compounds. If this material later becomes part of interstellar clouds, it could contribute to the formation of planets or even prebiotic chemistry in future stellar systems. This highlights the role of evolved stars not only as sources of heavy elements but also as potential contributors to the early chemistry of planetary environments. The velocity distribution of ejected material is also a critical factor in understanding the formation of the nebula. If the gas is expanding uniformly, it would suggest that the star has been losing mass gradually over an extended period. However, if velocity gradients are detected, with some regions moving faster than others, it could indicate episodic bursts of energy, possibly linked to a hidden binary companion or internal stellar instability. High-resolution spectroscopic studies will help determine whether the structure has remained stable or if it is actively evolving, with changes in brightness or morphology providing additional clues. Comparisons to other known stellar outflows provide valuable context for interpreting this structure. The similarity to bipolar planetary nebulae, which are often shaped by binary interactions, suggests that the nebula may represent an earlier stage of this process in a much more massive system. If future observations confirm the presence of an orbiting companion, it could provide strong evidence that binarity is a key factor in the formation of highly structured nebulae, challenging existing models of single-star mass loss. The possibility that the central star is approaching a terminal supernova phase adds an additional layer of urgency to ongoing research. If this is a pre-supernova system, then the surrounding nebula may play a crucial role in determining the characteristics of the eventual explosion. A dense circumstellar medium could shape the supernova's light curve, producing an extended afterglow or even influencing the type of remnant that forms. If the core collapse results in a neutron star or a black hole, the interaction between the compact object and the surrounding nebula could generate secondary emissions, including high-energy X-ray or radio bursts. Some researchers propose that this nebula represents a previously unrecognized category of structured stellar outflows, distinct from both planetary nebulae and classical supernova remnants. If so, it could mean that highly organized mass loss occurs in more stars than currently expected but remains undetected in systems with less favorable viewing angles. Advanced three-dimensional modeling, combined with data from next-generation telescopes, will be necessary to determine whether similar formations exist elsewhere in the galaxy. Long-term monitoring will be essential to track any changes in the nebula's structure. If subtle shifts in brightness or gas distribution are detected, it could indicate ongoing mass loss or dynamic interactions within the expanding material. Alternatively, if the nebula remains unchanged over decades of observation, it would suggest that its formation was driven by a past event rather than active processes occurring in the present. Either scenario will provide valuable insights into how massive stars shed their outer layers and how those layers evolve over time. The nebula's role in the broader astrophysical landscape extends beyond its immediate surroundings. If it is indeed an example of a structured pre-supernova outflow, it could help refine predictions for other massive stars nearing the end of their life cycles. Understanding the processes shaping this formation could improve models of how supernovae interact with their environments, potentially leading to better interpretations of historical supernova remnants observed throughout the galaxy. Future research will focus on uncovering the underlying drivers of the nebula's symmetry, whether they be magnetic forces, binary interactions, or unknown stellar dynamics. Upcoming missions and observational campaigns will provide increasingly detailed data, helping to answer fundamental questions about the role of evolved stars in shaping the structure of the interstellar medium. Regardless of what mechanisms are ultimately responsible, the nebula remains a rare and invaluable opportunity to study the complex interplay between stellar evolution, mass loss, and the physical forces that govern the cosmos. As observational techniques continue to improve, new details about this enigmatic formation will likely emerge, shedding light on the precise mechanisms responsible for its near-perfect symmetry. The role of radiation pressure in shaping the expanding gas is an area of active investigation, as intense stellar winds could be driving material outward along well-defined paths. If the star is emitting energy anisotropically, with stronger radiation in specific directions, it could be influencing the way ejected material disperses into space. This could help explain the structured nature of the nebula, particularly if interactions with a surrounding dust disk or magnetic field are reinforcing its geometric appearance. High-energy phenomena may also be contributing to the evolution of this structure. Some researchers suggest that the presence of shock fronts, regions where fast-moving gas collides with slower material, could be shaping the expanding nebula. These interactions create areas of increased density and ionization, altering how light scatters and giving the nebula its distinctive brightness distribution. If these shocks are being driven by periodic stellar outbursts, then the formation could be the result of multiple ejection events over time, each adding to the overall complexity of its structure. Infrared observations continue to provide new insights into the dust and gas composition of the surrounding environment. Data suggests that the dust grains within the nebula are relatively large compared to those found in diffuse interstellar clouds, possibly indicating that they have undergone significant processing due to radiation collisions. If this region is rich in carbon-based compounds, it could support the idea that evolved stars contribute not only to heavy element enrichment but also to the formation of molecular precursors essential for planetary system development. Determining the precise age of the nebula is another critical aspect of ongoing research. By analyzing the expansion velocity of different gas layers, astronomers aim to estimate when the initial mass ejection occurred. If the nebula is relatively young, it could be the result of a recent instability in the central star, whereas an older formation would suggest a more gradual mass loss process over an extended period. This distinction is important in understanding whether this structure is a transient phase that will evolve into a more diffuse remnant or if it represents a long-lived phenomenon sustained by continuous energy input. The potential presence of a binary companion remains a crucial question, as its confirmation would provide a strong explanation for the nebula's ordered structure. If a secondary star is orbiting the central object, its gravitational influence could be directing material into specific flow patterns, producing the observed symmetry. Some models suggest that if a white dwarf, neutron star, or even a black hole is present, accretion-driven outflows could be responsible for the formation's striking shape. Identifying subtle variations in the motion of the primary star or detecting indirect signs of a hidden companion through X-ray or radio emissions may help resolve this mystery. Further study of the polarization of light from the nebula will be useful in determining whether magnetic forces are playing a significant role in its evolution. If light scattering patterns indicate the presence of aligned dust grains, it could suggest that a strong magnetic field is guiding the expansion of gas. Such a scenario would align with models of magnetically collimated outflows, which have been observed in other astrophysical environments, including young stellar objects and active galactic nuclei. One of the most intriguing possibilities is that this formation represents an early stage of a process that has not been widely documented in astrophysics. If it turns out to be a precursor to a more well-known structure, such as a planetary nebula or a supernova remnant, it could provide a unique opportunity to study how these phenomena develop over time. Observing how the nebula changes in the coming years will be crucial in determining its future trajectory, whether it will eventually dissipate into the interstellar medium or continue evolving into a more complex structure. If the central star ultimately undergoes a supernova, the surrounding material could play a key role in shaping the explosion's observable characteristics. The presence of dense circumstellar matter could cause significant interaction between the supernova shockwave and the pre-existing nebula, leading to an unusually bright and prolonged event. If this occurs, it could offer direct observational evidence of how mass loss influences the final stages of massive star evolution. Long-term monitoring with next-generation telescopes will be essential in answering the remaining questions surrounding this extraordinary structure. Instruments capable of resolving fine details in the gas distribution, magnetic field orientation, and spectral properties will provide the data needed to construct a more complete picture of its origins and evolution. If similar objects are identified elsewhere in the galaxy, it may indicate that these types of structured outflows are more common than currently believed, potentially leading to a re-evaluation of existing models of stellar mass loss. Regardless of its ultimate fate, this nebula remains one of the most visually striking and scientifically valuable examples of how complex forces interact in the late stages of stellar evolution. Whether shaped by binary dynamics, magnetic fields, episodic outbursts, or a combination of multiple factors, its existence challenges conventional astrophysical theories and offers an unparalleled opportunity to study the intricate processes governing massive stars. Future observations will undoubtedly bring new discoveries, deepening our understanding of how these cosmic structures form, persist, and eventually transform into the next generation of celestial phenomena. As observations continue to refine our understanding of this extraordinary formation, the interplay between multiple astrophysical forces becomes increasingly apparent. The near-perfect symmetry suggests that a finely tuned combination of stellar winds, radiation pressure, gravitational dynamics, and possibly magnetic confinement is at work. Each of these factors contributes to shaping the expanding shell of gas and dust, maintaining its structural integrity over time. Whether this level of organization is an inherent property of certain types of stellar outflows or a rare coincidence of conditions remains an open question. Infrared spectroscopy has revealed variations in the temperature and density of different regions within the nebula, indicating that it is not a uniform shell but rather a complex, layered structure. This suggests that multiple ejection events may have occurred at different times, each adding a new component to the overall formation. If past eruptions have been episodic, possibly regulated by internal instabilities in the central star or interactions with an orbiting companion, the nebula could be an evolving record of its progenitor's mass loss history. The detection of specific ionized elements in the surrounding gas suggests that high-energy radiation from the central star is actively altering its chemical composition. Regions exposed to the most intense ultraviolet and X-ray flux exhibit signs of ionization-driven molecular dissociation, while more shielded areas retain heavier molecules and dust grains. This dynamic environment provides insights into how massive stars influence their surroundings, gradually enriching the interstellar medium with elements forged in their interiors. One of the primary challenges in understanding the nature of this structure is determining whether its symmetry is a transient feature or a long-term characteristic. If it is the result of a recent outburst, it may slowly degrade over time as the expanding material interacts with external forces. On the other hand, if it is stabilized by ongoing processes, such as a sustained mass flow or a persistent magnetic field, its geometry may remain largely unchanged for thousands of years. Tracking subtle shifts in the nebula's brightness and morphology over successive observational periods will be essential in distinguishing between these possibilities. Comparisons to other known examples of structured nebulae suggest that ordered mass ejections are more common than previously assumed. However, the degree of symmetry observed here is exceptionally rare, indicating that specific conditions must be met for such formations to arise. If future surveys identify similar objects in different regions of the galaxy, it could provide a broader statistical foundation for understanding how often these structures occur and what factors contribute to their development. Advanced numerical simulations are being used to model the potential formation scenarios for this system. By incorporating variables such as stellar rotation, Pulsation's gravitational influence could create flow patterns that resemble the nebula's distinct shape. If these models prove accurate, they could offer a new perspective on the role of binarity in shaping circumstellar environments. Another intriguing aspect is the potential for future variability in the central star itself. If it is nearing the end of its evolutionary cycle, further instability may lead to additional mass ejections or luminosity fluctuations. Such changes could provide direct observational evidence of how the formation is being influenced by ongoing stellar processes. If a sudden brightening event occurs, it could be a sign of an impending transformation, possibly signaling the transition into a Wolf-Rayet phase or even the approach of a terminal explosion. If the star ultimately undergoes a core collapse supernova, the surrounding nebula could play a critical role in shaping the aftermath. A dense pre-existing medium could result in an unusually energetic explosion, with shockwaves producing intricate interaction patterns within the already structured outflows. Such an event would be a rare opportunity to observe how massive stars influence their own supernova environments, offering insights into the processes that govern the final stages of stellar life. Long-term monitoring efforts will focus on detecting changes in expansion velocity, ionization levels, and thermal emissions within the nebula. Any deviations from the expected behavior could indicate previously unknown influences at work, potentially revealing new physics governing stellar outflows. With upcoming space-based and ground-based observatories providing increasingly detailed data, a clearer picture of this remarkable formation will continue to emerge. Whether this structure is an exceptional case or part of a broader, yet underappreciated category of organized mass ejections, its study is reshaping perspectives on how stars interact with their surroundings. The precise forces maintaining its near-perfect symmetry remain one of the most compelling mysteries in modern astrophysics, and future discoveries may provide the missing pieces needed to unlock its true nature. Regardless of what new revelations come to light, this nebula stands as a striking testament to the complex and often unexpected beauty of stellar evolution. The persistence of such a structured formation raises fundamental questions about the longevity of ordered nebulae and the mechanisms that sustain their geometry over time. If the observed symmetry is not merely a transient effect, then ongoing processes must be actively maintaining its precise form. One possibility is that the radiation pressure from the central star is continually shaping the expanding gas, reinforcing existing structures and preventing dissipation. In this case, variations in stellar output could lead to subtle but measurable shifts in the nebula's morphology, offering insights into how radiation-driven mass loss influences circumstellar environments. The presence of complex molecular compounds within the expanding shell suggests that chemical evolution is occurring on a large scale. As ultraviolet and X-ray radiation interacts with dust and gas, it triggers photodissociation processes that break apart existing molecules and encourage the formation of new ones. This cycle of destruction and recombination is key to understanding how massive stars contribute to the molecular diversity of interstellar space. If the conditions within the nebula are stable enough, they may support the gradual synthesis of increasingly complex compounds, further enriching the surrounding medium. Velocity mapping of the nebula's outflows is another avenue of investigation that may yield crucial insights into its formation history. If different layers of gas are expanding at distinct rates, it could suggest multiple episodes of mass ejection, each contributing to the overall structure. By reconstructing the motion of individual gas clouds within the nebula, astronomers can determine whether the expansion is accelerating, slowing down, or maintaining a steady rate. A uniform velocity distribution would support the idea of a single, well-coordinated outflow event, while irregularities could indicate ongoing dynamic interactions between different layers of material. The role of external influences, such as interactions with the surrounding interstellar medium, is also worth exploring. If the expanding nebula is encountering regions of higher density gas, it could be experiencing external pressure that helps define its shape. This scenario is particularly intriguing because it would imply that the large-scale structure of the interstellar medium plays an active role in shaping stellar remnants. If such interactions are confirmed, they could offer a broader context for understanding how similar nebulae form across different galactic environments. Advances in computational astrophysics are enabling the development of increasingly sophisticated simulations that attempt to recreate the conditions necessary for such a structured formation. These models incorporate factors such as stellar rotation, magnetic field dynamics, radiation transport, and binary gravitational effects. The goal is to determine whether a single dominant force is responsible for shaping the nebula or if multiple factors are working together in a complex interplay. Early results suggest that while radiation pressure and magnetic fields alone can produce organized outflows, the addition of a binary companion significantly enhances the likelihood of maintaining long-term symmetry. If a compact object is present within the system, it could further complicate the dynamics of the nebula. A neutron star or black hole companion could be influencing the surrounding material through accretion-driven winds or relativistic jets. These high-energy processes could create additional structure within the nebula, potentially explaining regions of enhanced brightness or density variations observed